And we'll move to our second speaker, Chelsea Sutherland. Chelsea, the floor is yours.
There we go. Can you see everything okay, Ken?
Yeah, that looks good, Chelsea.
Perfect. Okay, thank you for the introduction. So today I'll be sharing with you all what I've been working on for my master's thesis. And the title of my thesis is Quantifying the Carbon Sequestered in 25 Years of Herbicide-Tolerant Canola Production in Saskatchewan. So as a bit of an introduction, the Canadian ag sector emits about 10% of Canada's national greenhouse gas emissions, and carbon dioxide represents about 80% of these national emissions. Farmers have been progressively shifting towards more environmentally friendly practices in recent decades. These include adoptions of no-till and minimum till, and away from practices such as conventional tillage and summerfallow. There's a number of reasons for these shifts. A key one is that farmers were trying to minimize soil erosion in their fields, and this was a big problem in the mid-1900s. Farmers were also trying to improve soil moisture and soil quality in general, and also trying to minimize the equipment passes made across their fields. There were also a number of technologies that helped farmers to make these adoptions. Innovations in seed technology, fertilizer, and chemical assisted farmers in these shifts. And there's also ample literature which indicates that the introduction of herbicide-tolerant canola in 1995, especially in Saskatchewan, facilitated these shifts as well by providing farmers with more cost-effective and efficient weed control. The adoption of these practices helped to improve soil carbon sequestration by reducing soil disturbance and increasing crop residue levels. And just as a note, soil carbon sequestration is when carbon is removed from the atmosphere and stored in soil storage pools, and this happens through photosynthesis. Soils can be either net sources or net sinks of carbon. Saskatchewan ag soils have actually become net sinks in recent decades due to soil carbon sequestration. Shaping policy in a way that supports ag production and at the same time helps to improve environmental sustainability requires the effects of these management practices to be quantified. So that leads me to my main research problem. How has carbon sequestration in Saskatchewan ag soils changed as a result of the adoption of no-till, minimum till, and the elimination of summerfallow since the introduction of herbicide-tolerant canola in 1995? So we use 1995 as a baseline for two reasons. Number one, as I mentioned earlier, herbicide-tolerant canola did contribute to the adoption of these practices that farmers made. And also it helps to capture the rapid and widespread adoptions that occurred in the early 90s. So I'll address this research problem through four objectives. Analyze the long-term changes in farm production practices since 1995. Determine if and to what extent these herbicide-tolerant cropping systems impacted farm management changes. To quantify the change in carbon sequestered in this 25-year period, and then to calculate an estimated economic value of the sequestered carbon. For today's presentation, I won't be focusing on objective number 2, just for the sake of time, and it's not a part of my sequestration model, but I'm happy to discuss it after the presentation if you have questions. And just one more thing to note, in my research problem, I've decided to focus only on carbon sequestration. I acknowledge that nitrous oxide and methane are also important and potent greenhouse gases in agricultural production as well. However, the whole emission cycle is just beyond the scope of what I'm addressing in this thesis. And in addition, recent policy discussions about the increase in the carbon tax and the federal carbon offset program helped to make my decision to focus on carbon in this study. So to collect the data for my analysis, I surveyed Saskatchewan farmers on farm management practices during 2 time periods. So the first was prior to 1995, and the second was in the most recent crop rotation. Surveying farmers on practices that they used 25 years ago certainly creates room for recall bias. So how do we know that farmers will remember the practices that they used 25 years ago? We address this bias two ways. The first is that I benchmarked all of the management data I collected from these farmers against Saskatchewan crop insurance data and also the Canadian Census of Agriculture data, just to make sure that I was accurately capturing the management trends that occurred during this time period. And the second is that we encouraged farmers to use farm records to answer these questions if possible. And 80% of participants did indicate that they used past farm records to answer these questions. We recruited farmers for the survey through a variety of avenues in order to try to reach a broad demographic of farmers, especially different ages of farmers. So we used newspaper ads, radio, the Saskatchewan commodity groups, Saskatchewan Agriculture Grads Association helped us, the Saskatchewan Ministry of Agriculture, and we also sent word out through social media and just word of mouth between farmers across the province. The survey was made up of 4 components. The first one followed the seed through until harvest time, and then we looked at fertilizer, tillage, and chemical use separately. We also asked farmers to comment on how various innovative technologies helped them adopt these sustainable practices. We had hoped to host in-person workshops last fall to have these discussions with farmers because the survey is quite lengthy and complex, and we thought it would be easier to answer questions this way. However, due to last fall's provincial COVID-19 restrictions, we had to move survey participation to online. All survey participants were paid $200 if they completed the survey, and it took about 3 to 4 hours for completion. The framework I used for my analysis is a carbon accounting framework. These systems are commonly used to estimate net greenhouse gas fluxes, so they've been used in a variety of studies, some of which I've listed here. And systems like this are also used in Canada's national greenhouse gas inventory reporting, which occurs on an annual basis. My specific model is adapted from the Prairie Crop Energy Model. This was developed by Cecil Nagy in 1999. And then my specific model I use was adapted further from Smythe and Awada's version in 2018. My model separates the province into 9 separate regions. And based on my sample size, I actually aggregated these regions to the semi-arid and the subhumid prairie for most of my analysis. And the carbon coefficients that I used in my model were developed by Agriculture and Agri-Food Canada for Canada's national inventory reporting. And at the time of my study, these are still the most up-to-date coefficients used in these reports. So here's a snapshot of the carbon accounting models that I used in my study. So there's 2 separate accounting equations. The top one looks at the carbon sequestration from changes in tillage practices, and the bottom looks at the changes from summerfallow practices. I'll explain why I use 2 separate equations in a few slides. So these equations essentially aggregate the sequestration effects across the 9 regions, and the sequestration is calculated using the area under the cropping practice in terms of hectares, the carbon sequestration rate of the cropping practice. So these are those carbon coefficients that I mentioned. The next variable looks at the residue of each cropping practice, and this is calculated using a relationship between the crop yield and the harvest index. This is a very important variable because these carbon coefficients, they assume that there's medium carbon input in all situations, and this variable helps me to account for above average and below average crop yields. The next is the rate.
Sorry, Chelsea, you're getting a lot of, I think Mohammed Garbani, I think you're causing there's a lot of feedback. Thank you very much. Sorry, Chelsea, go ahead.
No problem, thanks, Ken. So the RR variable is the rate of carbon input to the soil from these crop residues. This is taken from Maillard et al. In 2018. And the final variable is actually a dummy variable, and it accounts for crop residue removal techniques. So essentially, if the farmers remove the residues from their field, we assume there's no positive sequestration effect. And so it's assigned a value of 0. And if they leave the residues in their field, it's assigned a value of 1. This is just showing the carbon sequestration coefficients that I used. They're discussed in terms of metric tons of carbon per hectare per year. One thing to note is that soil productivity is typically higher in the subhuman prairies, and therefore they have higher sequestration coefficients. And another thing to point out is that practices that actually emit carbon rather than sequestered on average have negative carbon coefficients. So that includes conventional tillage and the inclusion of summerfallow. Finally, I'll discuss 3 valuation scenarios that help me to create upper and lower bounds on my economic estimates. So the first is the online NORI carbon removal marketplace. This is a newly developed marketplace in which farmers are paid for the removals of carbon that they have, and emitters or just interested citizens can purchase these removals from the farmers. And this is assigned a value of $19.86 per metric ton of CO2 equivalent in 2019 Canadian dollars. The 2019 Canadian federal carbon tax had a value of $20 per metric ton, and the social cost of carbon. And this is a valuation that represents the monetary damage from 1 additional ton of carbon being emitted in a year, has a value of $45.89. This slide just shows the participant demographics for my survey. So I had 107 participants complete the survey by the end of January. 55 of these completed the early time period, and then 104 completed the most recent time period. I compared these demographics to the average farmer from Saskatchewan in the 2016 Ag Census data. On average, the farmers in my study were younger and had achieved higher post-secondary education and also operated larger farms than the average farmer in the census data. There's a couple of reasons why I think this might be. The first is that the younger farmers just may have been more comfortable with the online delivery of the survey that we had to go to. Also, those farmers who achieved higher post-secondary education themselves might have been more inclined to participate in an academic survey like this. And finally, literature shows that larger farm sizes actually might have been more early adopters of these various innovative technologies in efforts to improve efficiencies and cut costs. And so those farms who were early adopters of these technologies might have been more willing to participate in a survey that asked them to comment on these technologies. This slideshow, I have to say thank you to Savannah for helping me put together this image. And this just shows the spread of my participants across Saskatchewan by the RMs in Saskatchewan. And so as the color moves from cool to warm, it just shows the number of participants from each RM who participated in my survey. But overall, we had a pretty good representation from all corners of the province throughout my survey. Before I jump into my results, I did have to make 5 key critical assumptions with my model. The first is how I classified tillage definitions. This is quite variable in the literature. It can depend on the tillage implements used, the number of passes, it can depend on the climate, and the crop residue levels remaining. But based on the studies that my model is most closely based on, I assume that conventional tillage is 1 or more cultivations in the semi-arid prairie and more than 1 in the subhuman prairie. Minimum till is 1 cultivation in subhuman prairie and harrowing in both regions. And no-till is only direct injection of seed and nutrients. The second assumption I mentioned earlier, if crop residues are baled or burned and therefore removed from the field, there's no positive sequestration effect from the residues. On average, there was only 18% of participants who removed their residues in the early 90s, and only 2% from 2016 to 2019. So this assumption only affects a small part of our sample. Number 3, we assume that there's no interactive effects between the carbon sequestered from changes in summerfallow and the carbon sequestered from changes in tillage. And this is why I had the 2 separate equations in my model. We know that there are likely interactions between this sequestration because these are complementary practices in general. However, the value of this interaction hasn't been studied enough to determine what it is in the literature. So for my analysis, we just look at the effects separately. Number 4, I assume that all regions of the province have equal levels of sequestration potential. The potential for sequestration depends largely on the initial levels of carbon in the soil. However, this information wasn't available across the province in 1995, so therefore we just assume equal potential. And number 5, we assume that the changes in adoption practices occurred relatively linearly and are permanent, unless the data indicates otherwise. Because we only have information from the 2 time periods, but not what happened between the 2 time periods, we don't know the trend of these patterns when we don't have the data for them, so we have to make this assumption. So I'm just going to provide a very quick overview of my results. Just based on time, I won't go into too much detail, but I'm happy to answer further questions. So this first graph just shows the changes in management practices that occurred. So in this 25-year time period, hectares without summerfallow in their crop rotations increased by 47% to almost 100% of hectares. Conventional till hectares decreased by 52%, minimum till hectares increased by 4%, and no-till hectares increased by 48%. So we can see some huge swings in management practices here. As I mentioned earlier, I benchmarked this management data against Saskatchewan crop insurance data and the Canadian Census of Agriculture data, and the trends among the 3 databases were very similar. So this graph just shows you my calculations for the carbon sequestered from changes in tillage practices, and they're discussed per total hectare of crop production under study. So if we move left to right across the graph, we see the changes in sequestration from the changes in no-till practices, from minimum till practices, the changes in carbon release from conventional till practices, and the far right column gives us a look at the net carbon sequestered per an average hectare in these time periods from changes in tillage practices. So in the early 1990s, the typical hectare in Saskatchewan would actually be emitting 0.028 metric tons of carbon per year from tillage. But by 2016, this same average hectare would actually be sequestering 0.123 metric tons of carbon. We do a similar analysis for the carbon sequestered from changes in summerfallow practices. Again, the net carbon sequestered per hectare is the difference between the net carbon sequestered from the removal of summerfallow and the net carbon emitted from the inclusion of summerfallow. So in the early 90s, we can see that the average hectare was emitting or sequestering a negligible amount of carbon. And this is because about half of the hectares had summerfallow management. But by 2016 to 2019, 0.419 metric tons of carbon were being sequestered per hectare from the removal of summerfallow. This graph just takes these estimates and applies them to a hypothetical 1,000 hectare farm to illustrate how sequestration from a farm would have changed during these time periods. So in the early 1990s, a typical 1,000 hectare farm would have been emitting about 28 metric tons of carbon per year from tillage. But by 2016 to 2019, the same farm would be sequestering 123 metric tons of carbon. Similarly, for changes in summerfallow practices, this 1,000 hectare farm would have been sequestering about 5 metric tons of carbon per year. And by 2016 to 2019, this had changed to 419 metric tons. To put these results into context just a bit further, the average Canadian car burns about 2,000 liters of gas per year, and this equals 4,600 kilograms of CO2 per year emitted. If we use a ratio of CO2 to carbon, which is 3.667, this equals about 1.25 metric tons of carbon emitted annually. The same hypothetical 1,000 hectare farm would be emitting about 22 times more carbon per year than the average car from tillage in the early 90s. But by 2016 to 2019, this farm would actually be sequestering carbon emissions from 98 cars from conservation tillage practices. Similarly, from the removal of summerfallow, In the 1990s, the same farm would have been sequestering emissions from 4 cars per year, but by 2016 to 2019, from 336 cars from the removal of summerfallow. And just finally, I applied the economic valuation scenarios to the change in carbon sequestered from this 1,000 hectare farm. So if we use the upper and lower bounds on these estimates, the change in annual carbon sequestration over this 25-year time period would be valued between close to $86,000 to almost $200,000 from changes in tillage practices. And from changes in summerfallow practices, the change in value ranges from almost $295,000 to $681,000. And this is just from this 1,000 hectare farm. So what do these results mean? They have a couple industry and policy implications. So there's currently some industry groups advocating for changes to the carbon tax and the federal carbon offset program. These include the Saskatchewan Soil Conservation Association, the Western Wheat Growers, the Saskatchewan Agriculture Association of Rural Municipalities, and this is just a few of the groups. My results help to provide a portion of the data that they need to support their positions. Of course, my research can only comment on carbon sequestration. It can't comment on emissions or the other greenhouse gases. Further and more consistent research would be required for this. However, it does help to provide a start for these positions. Number two, it contributes to the potential for branding of agriculture as sustainable. This is something that has been done in the Canadian beef industry. Jose touched on this earlier, through the Sustainable Beef Production Standard, and in the American soybean industry with the Sustainably Grown U.S. Soy Project. Again, my research can only contribute to the sequestration portion of these metrics. However, again, it does provide a start. Finally, there's opportunity for consistent future data collection through this survey to help create a database of changes in practices. And this will actually help to eliminate the recall bias that I discussed for future studies, because farmers will only have to fill in their information for, let's say, every 5 years, if this is the time period that we use for this study. I'll conclude with just a few limitations of my study that I recognize. First of all, I'm only looking at one small component of the greenhouse gas emission cycle. To look at the whole cycle of emissions, we would need nitrous oxide, carbon dioxide, and methane. And we'd also need to consider indirect emissions, such as the production of inputs and transportation. Number two, my calculations are based on these broad empirical estimates. So I'm talking about these carbon coefficients. It's very difficult to physically measure changes in soil carbon levels, especially over long time periods. So in models such as this, we're limited to these estimates. Number three, I have a relatively small sample size based on the population of Saskatchewan grain farmers. Number four, I'm limited to the information provided by farmers between the 90s. As I mentioned, this recall bias. Using the farm records does help to minimize this. However, our data is only as good as the farmers provide. And number five, I'm only looking at these 2 time periods, but not the 25 years between these time periods. So I don't have data on the timeline and consistency of the farm management changes. So thank you all for listening. I want to thank my Dr. Stuart Smythe, Dr. Bill Kerr, and Dr. Peter Phillips, who are my committee, and I'm happy to have some questions.
Thanks very much, Chelsea. We'll open it up for questions now.
I have a question, Chelsea.
Yes.
2 questions, actually. Thanks very much for your presentation. Very interesting. My main question is about the other greenhouse gases. You gave 2 reasons for not wanting to include them. The first one was that it gets a little complicated, which I understand. There's a lot of moving pieces here. But I wanted to point out that the model that you're using, this derivative of the prairie crop energy model, that was actually constructed to account for all of those greenhouse gases from the beginning. So Is there a reason why you can't also include those coefficient changes from management practices?
Yeah, that's a good question. And it's something I could definitely further with further research on this. I just took the sequestration portion of this model. There's different accounting equations for the different greenhouse gases, and that certainly could be expanded on. It's just not something that I included in my research question.
Okay. The other reason you gave is that, the current policy, the current carbon tax policy isn't really focused on those emissions, which is kind of true, but one thing to keep in mind is that Environment, Climate Change Canada, the government of Saskatchewan, Ag and Agri-Food Canada are right now looking for ways to provide subsidies to farmers for taking on practices that will reduce all types of greenhouse gas emissions. And because Saskatchewan farmers have done such a good job sequestering carbon already, there's actually not a whole lot of room for improvement in that area relative to these other areas. So I think it's actually maybe backwards to say that because of the policy you're not considering it. I would say that because of the way the policy is going to be developed, you should consider it. So it's just some advice, I guess.
Thank you, Tristan. I appreciate that.
Yeah. The second and last question I had is that, this is a pretty expensive undertaking, $200 per respondent, plus the extra advertising, all those types of things. Could you maybe provide us some information about who funded this study?
I might need Stuart's help on this, but I'm pretty sure it was the P2IRC for most of it. The PERC project funded this crop rotation study. And then, of course, it's also funding. Jordan is working on this project as well. And there'll be a number of other research papers that we developed from this survey. My thesis was only a small portion of this research project.
Oh, very cool. All right. Thanks, Chelsea.
Yeah, so Tristan, it's part of the funding for Chelsea's work came from the PERC project, and the balance of it is coming from the funds from my research chair.
Thanks, Stuart.
I think we have a question from Eric.
Hi, Chelsea. Thanks for the presentation. One question I have, I noticed, you're looking at these two time periods, 91 to 94, and then 2016 to 2019, and a good chunk of your respondents are under 35. So they probably weren't the main decision maker in 1994, but maybe they had access to that data, maybe not. But I guess my question is, did you run this with kind of excluding them just to see if your estimates are stable when you look at maybe the respondents that were the decision maker in both time periods, just to maybe but the other way, maybe the under 35 might have better data because in order to answer that, they need the actual record to fill that out. So I guess my question is, did you split that and see how the results change or don't change?
Yeah, thanks, Eric. That's a good question. I'll answer that in two parts. The first one is that a lot of younger participants emailed us and asked if it's okay if they're the main participant, but they work on it with their dads and their grandpas, and so they kind of do it as a generational survey. So the participant who entered the demographics might have a younger age, but they might have been working with their parents to answer this. But secondly, I did do the test of just this participants who answered both time periods compared to the total demographics. And when I ran some t-tests, there was actually no significant differences between the two samples.
Okay, thanks.
Additional questions for Chelsea? Maybe I have a quick one, Chelsea. You showed that map and showed that you had respondents from a pretty good cross-section of the agricultural zone of Saskatchewan. I'm just wondering, and maybe your coefficients did this, but the sequestration rate in the brown soil zone is dramatically different than the sequestration rate in the black soil zone. Is there a way for you to, I understand your reporting of averages, that's the way to do it in a context like this, but for your thesis, is there a way to sort of tease out what the results might look like in the brown soil zone as compared to the dark brown, as compared to the black?
Thanks, Ken. That's a good question. I actually didn't do that by soil zones, and that's definitely something I could look into. I did aggregate it just to the two regions that I discussed, so the subhumid region and the semi-arid region, which do have different soil types on average to begin with. And in my thesis, I do have the results split up by that just to show the comparison, but not specifically by soil types.
Okay, yeah, because it is an interesting. I mean, I know some of the research that's gone in the past, and this is, some of this is pretty old, but looking back at you know, in the brown soil zone, for example, with a summerfallow situation, the yields are greater, and so potentially there's greater carbon going into those soils sometimes than with a more sort of zero till situation. So there's some nuances there, I think, in the different soil zones with respect to what their capacity is to sequester additional carbon, I think. So it might be worthwhile a mention, I guess, is beyond anything else.
Right. Thank you, Ken. I'll look into that.
Additional questions for Chelsea? Seeing none, I'll thank you, Chelsea, for a very good presentation, interesting discussion. Looking forward to seeing the thesis when it's all done, which I'm sure will be happening fairly soon. So, so overall, I want to thank Jose and Chelsea for their presentations today. They're very good presentations. Looking forward with respect to seminars, there is no scheduled Friday seminar next week. However, we will have two of the candidates for the Van Vliet term professorship are here Monday through Thursday, so there will be a couple of seminars and a couple of teaching presentations during that week, and then there is a scheduled seminar again on Friday, April 30th. So thanks everybody. Have a great weekend. Thank you, Chelsea and Jose.